Do we have any questions on exam 2 material?
Question
25? Know how to determine and compare the dipole-dipole interactions between two different molecules. So if we have, let's say, if we have trying to think of an example. CH3, CH2OH, for example. And we have a CH3OH. And CH3, CH2, CH2, OH. So this is an example. Which one, let's see, compare the dipole-dipole interaction. Which one has a stronger dipole-dipole interaction? A, B, or C? A, B, or C?
This is CH2, CH2, CH2.
Yeah. Any ideas?
Dipole, I think they're A.
So that means between the molecules, actually this one's hydrogen bonding, but which is a type of dipole-dipole, right? So out of these three, which one has a stronger dipole interaction?
Oxygen and hydrogen C.
That's right.
C because it's which hydrogen can each have it.
Okay, so here we go. They all have an OH bond, right? So that's going to make it, in this case, hydrogen bonding, right? Or we can call that a rare or a strong dipole-dipole interaction, right? What's this? The CH part. What type of intermolecular forces do we have for the CH portion? What? It is nonpolar, so what is the type of intermolecular force? London dispersion force. So which one do we have more London dispersion forces? C. Therefore, this would be less dipole interaction. That means this one's the most. You with me? Because they're almost the same elements, same whatever.
So C is better.
C is a stronger dipole interaction. I mean B. Yeah.
C is the stronger one.
B is the stronger dipole interaction. C is the weakest because it has a lot of London dispersion in there.
C is better.
Because this part right here is nonpolar, right? And you got a little portion that's polar. So it's mostly nonpolar.
So C is B is the correct answer.
Does it make sense why?
Because it has 3 hydrogen bonds.
Because this has less carbon-hydrogen bonds
That's not
compared to these two. We good? And I'm giving you this big, huge organic compound here. Why is it okay that I give you this? Because I tell you its structure right here. This is how it's structured. Otherwise, I would just write it C2H6O, right? I'm not gonna ever give it to you like that if I give you this big compound. Yeah? Are we clear on that or no? Okay? What else? Yeah, you bet. Oh, no other questions? We're gonna move on? Oh. I'm just teasing. Go ahead, Andrew.
I have, let's see, hard time with polyatomic ions. I was doing the worksheet. Let me find an example.
This is
Yes. So let's see, just determining the charge of each atomic or polyatomic ion. Sorry. So KCl04.
which number?
So
And what do you need to determine?
the charge on each ion.
Okay.
So
So potassium is one ion. How do we know?
Because it's on
Because that's the metal, right? Metal, that's the cation. Therefore, the rest of it is the anion. And you have to either know this or you better have it on your little reference card. But I would highly encourage you to get these down because after this unit, you're going to want other stuff on there, right? So what's the charge of ClO4? And potassium is a
positive.
1+ because it's in group 1. Did that answer your question, Andrew?
actually, yeah, I just realized what I was doing wrong. So maybe that's not the best example. Sorry.
Are you wondering about one with
Well, because I think what
transition
I did
metal
was
in
I
it?
saw the 4, and I was like, wait, how does the 4 work into? Because wouldn't that make
It doesn't.
4 potassium?
No.
Yeah, I think at first
because
that's
there's
what I did.
no parentheses. And that's what a lot of people do when they're first learning this stuff. They forget about, okay, there's that number there,
One, yeah,
but there's no parentheses. That means there's only one of them,
right.
okay?
Um,
So if we have CuSO4 and we got to write its name, do y'all remember how to do this? Since we have a transition metal, we got to know its charge, right? And I like this one because I don't like to confuse people, but a lot of people have misconceptions on this particular one, or one like this. So what do we do to figure out the charge of copper? We got to know what? The charge of the other ion. What's this other ion called? Sulfate. And what's the charge of sulfate? 2-, good. Or -2, And so what's the total charge of all of the anions put together? And why do we have to do this, guys? And this is just a process. The reason we do is because the total charge of this compound is neutral, right? If we have negatives, we better have some positives with the same amount so that they neutralize out, right? So what's the total charge of all the sulfates? -2, not -8. Because there's no parentheses, that means there's only one of them, right? This side has to be +2. There's only one copper, so it takes all of the charge. So this is copper, Roman numeral 2, sulfate. Good? Yeah. Lucas.
Is there any other way to determine the charge of something like sulfate without just knowing it? Like, could you do a Lewis structure thing to determine that, or is that something you just have to know?
Let's see. I mean, if you knew it was SO4 and you wanted to know its charge, I guess you could draw the Lewis structure. And here's how you determine that. We didn't really discuss formal charges here, but you could. Do you want me to show you?
Sure, yeah.
Okay, so if we know it's SO4, but we don't know its charge, then we count valence electrons. We have 6 plus 6 times 4, that's 24. That's a total of 32 electrons. Did I count wrong? 30. Always count right. Okay. Sulfur with 4 oxygens. 2, 4, 6, 8. We have 22 left. Did I count those right? Yeah, okay. So 4, okay. 2, 4, 6, 8. We have 22 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, we can't have. Did I count wrong? Be something like, no.
But because you have 2 electrons unaccounted for, wouldn't that make sense why it's 2 minus?
Oh, yeah, we have 2 extra, yep. So, and again, it's just a guess, right? But, so yeah, we don't have, we have too few to have all octets. Then I don't like that method. I would just know them. That would be the best way. But yes, you could do
I
that.
remember when you did the T43
Uh-huh.
demonstration, you showed the charges
Yeah,
on each.
perfect. That's a way to do it without, I mean, that's a way to use the periodic table to guide your thinking.
Yeah.
Uh-huh. If you know that, if you don't, make sure you have them down. And if you don't have them down, you're gonna take the test, I would definitely put them on that card for this time. Then don't put it off. Still get them down. Still learn them. But if worse comes to worse, I would do that. Okay? Yeah, Andrew.
So along with the polyatomic ions, I can do an example of determining the appropriate name for the following chemical formulas.
Okay?
So for example, nickel acetate.
It's called nickel acetate.
Yes. So Ni, and then parentheses,
C2H3O2. Oh.
Parentheses, and then 2 of those.
2 of them? Okay. Oh yeah, so this is the same thing we did here, or here, right? Since this is a transition metal, we better find the charge of it. And what's the charge of acetate ion? It is -1. And this is what we gotta know, guys. Gotta know this. So -1 times 2, because there's 2 of them, because there is a parenthesis, right? That's -2. This side has to cancel out the -2, so it has to be +2. And there's only 1 of them, that means it's a 2+ ion. Therefore, the name of this is called nickel 2 acetate. Question? No? Didn't click?
I don't know why these weren't clicking when I studied it, but now it just seems.
Oh, but it's good?
Yeah.
Okay. Yeah, that
So
is good.
Can we do one more just to be sure?
Yeah.
So AgCN. Sign.
Okay. All right. So silver is a transition metal. It's a special one. Whether or not you have to know that for the test, I can't remember. But, so what do we need to know about silver? You don't have to know it. You could still find it out this way. So let's do it. What's the charge of cyanide? 1-. And how many are there? Just 1, so that's a total charge of -1. This side has to be +1. You with me? And there's only 1, that means it's +1 charge. So this one we could call silver 1 cyanide, but silver is always +1. Silver's kind of an exception. But again, if you don't want to memorize those exceptions, then call it silver 1 cyanide. That would be okay. Well, as far as in my mind, it's okay. I don't think that one is on the test for you to actually know that. So if it was called silver cyanide, that's the proper name, because there's only one charge for silver. Did I talk about the other charges? The other transition metals only have one charge? Silver, what are the other two? Zinc and cadmium. Okay, we did talk about that. Good. Yeah, Chad. Oh, let's see. Hold on. Mariana, you had a question? I was going to get to you after this. Sorry, Chad. Number 7 on the study guide? It says, know how to tell if the formula is incorrect for an ionic compound. So, tell me this. Is that a correct formula for aluminum oxide? Well, how do you tell? Well, aluminum, do we know the charge of an aluminum ion? Al3 plus. Do we know the charge of an oxide ion? Do you have to memorize this? No, look at the periodic table, right? Do you know how to find this on the periodic table? Yes? Okay. Now what do? Cross the charges, cross the numbers anyway. Al2O3, this is what it should be, so this is incorrect. So you actually have to do it and figure out, okay, is this right? Yeah. What about, is that one correct? Why don't you figure it out? Because if I do this, that helps me. Make sure you can do this.
Quick question about the aluminum.
Okay.
We know the charge of aluminum because it's not a transition metal.
That's right. Yep.
It's like on the right.
Yep, it's the main group element. It's in group 13, so it has to lose 3 electrons to be like, is it neon? Yeah. Uh-huh. Yep. So what's the charge of magnesium? 2 plus. What's the charge of oxygen? We cross them, and what do we get? Mg2O2. Is that the right one? No, because we have to simplify. So this one is correct. Does that make sense?
Which one is correct?
What?
Magnesium is correct, yeah.
MgO is correct formula for magnesium oxide.
They cancel each other.
Yep. Yep.
Number 3.
Number 3. Now know how to name ionic compounds with main group metals. Main group metals, how do we name the cation? Here's a ionic compound with main group elements in it. How do you name the cation? How do you name this thing? Yeah, just use the element name, aluminum. How do you name the anion? Change the Ne to IDE, aluminum oxide. Yeah. So here's an example. Aluminum is the name of the first of the cation. Change the ending of the second one to IDE, or the anion to IDE. That's how you do binary or ionic compounds with main group elements. Aluminum oxide. Yep. Yeah, Chad.
Is it okay if I ask something not related to this?
Did that answer your question, Amon?
Yes, I got
Okay, yeah, go ahead.
So with solids,
Mm-hmm.
we have that kind of range with covalent solids at the bottom and then covalent network solids on the top.
Yep.
The higher you go, the higher melting point it is, right?
Yeah, so if we do covalent compounds, what's the next one? Ionic,
Ionic.
then metallic,
Metals, yeah.
and
CVS.
covalent network.
CNS, sorry, not CVS.
Yeah. So this is less melting point. This is high melting point.
However,
We could say this is softer. This is harder. Right?
remember from my notes, it does say that ionic has the strongest IMF, so, right? Strongest intermolecular.
Yeah, the ionic compound has the strongest intermolecular force. So what makes metallic and covalent network stronger?
For metals, it's the C of electrons.
Uh-huh.
And for the covalent network solids, they're just more compact, right?
It's a covalent bond. An actual bond is stronger than all intermolecular forces. Because these guys don't really use intermolecular forces. Good?
Yeah.
Any other questions? Yeah, Lucas.
Yeah, can we go over number 11 for
Yeah.
determining unknown ions with a given formula?
Yeah. So if we have X, well, let's see. I have a periodic table here. I won't touch that for a minute, it's all broken apart. Let me just think in my mind for a second. Where the X ion,
It's disconnect.
oh, it's not working? Oh.
You press the button.
Is someone else trying to get in here? Okay. I don't know. All right. X ion has, let's see, 23 electrons. Sorry, I might have done this one in class, but I guess I could pick a different one. Is this one okay? Okay. Has 23 electrons. Figure out what X is.
This is
Okay. So what kind of compound is this, guys? Ionic or covalent? How do you know it's covalent?
There's oxygen.
Ionic compound's going to have oxygen in it. Because an ionic compound is a metal and a nonmetal, right? So let's see, is this ionic or covalent? We don't know what X is.
We can cross.
X is an ion. Hence, this is what? An ionic compound. You with me? All right. Guys, so that means we need to know what the charge of what one? X. Of the one that we don't know, right? Let's find out what the charge of X is. How do we do this?
Cross.
Oh, we did this before, right? Several times this morning even. This may or may not be a transition metal, but we still don't know its charge, so we better find it. So what is the charge of oxygen? 2 minus. How many are there? 3 of them. That's a total of -6. So this side has to be a total of +6. You with me? Do we all understand this process? Yes or no? Tell me if you don't. No? Okay? All ionic compounds must be neutral. They must be. So if we can find the total charge of the anions, then the total charge of the cations has to be the same, just opposite. Right? So we know the charge of oxygen ion to be -2, and there's 3 of them. So each one has a charge of -2, so -2 plus -2 plus -2, or -2 times 3. You with me? That gives us -6. That means the total charge of all the cations has to be +6 for this to be an ionic compound, and we know it is. Well, since there's 2 of these cations, what do we have to do with this total charge?
Cancel.
Divide it by 2. Divide it equally into 2 because these are the same. They're both x, or whatever it is, right? So what's the charge of x? 3 plus. You with me? Any questions up to that point? All right, so we know that the X ion, or we could just say X3 plus, has how many electrons? 23. It tells us right here in different words, right? 23 electrons. Okay, so how many does X have? 26. It had to lose 3 to become 3 plus. Are you with me? Anybody not understand that? Because this is what you do need to understand. And this is the whole purpose of this type of problem. To help you to understand, well, if it's a plus ion, that means it lost electrons. If it's a minus ion, then it gained electrons, right? So this has 26 electrons. And if the charge is neutral and it has 26 electrons, how many protons does it have? 26, same number. Oh, and that tells us what? The atomic number. So you find 26 on the periodic table, and this is what? Iron. You with me? Yeah.
We have a periodic table available in the exam.
That's right. Yep. Yep. You will be given one in the testing center, along with the electronegativity chart. Yep, you'll be given that. You guys have that periodic table that I gave you? Okay, that's the one that you'll get in the testing center.
She says question 14.
Amon has a question, number 14? Okay. All right, number 14. It's okay to have questions, no problem. Know how to draw the Lewis structure for a covalent compound. Do we draw Lewis structures for ionic compounds? No, we don't. So, essentially, we just need to know how to draw the Lewis structure, right? What do you want to draw it for? A polyatomic ion? That's covalent, right? Just the ion itself. Or do you want to do a different? And again, I'm only going to have you do this for binary covalent compounds. Ones with 2 atoms. So what example do you want? One of each? Okay. So let's do CO3 2 minus. What's this called? It's a polyatomic ion. What is it? Carbonate. Okay. So what do we do to find? You tell me. What do we do?
We draw the
Determine what? Number of
proton.
valence electrons, right? To draw the Lewis structure, we got to know how many valence electrons it has. So how many does carbon have? Does everybody know how to find this on the periodic table? These are main group elements. And for all binary ionic compounds, in fact, covalent compounds, they're all main group metals, or nonmetals, right? Nonmetals are all main group. So we can figure out how many valence electrons they have. How many does oxygen have? 6, and we got to multiply that by 3. What do we do with this charge? Negative means we added, right? Gained electrons. So we gained 2 electrons. So that's a total of 18, 2024. Good? Now we got to determine what? Which atom is the central atom? Which one is it? Carbon or oxygen? Carbon. And we have 3 oxygens hooked to it. How many electrons have we used so far? 6 electrons. So that means we have 18 left. Where do we put them? Oxygens, 2, 4, 6, 8, 10, 12, 14, 16, 18. We used them all. Don't use any more. I know carbon wants 2 more, right? Because it doesn't have an octet. So what do we have to do? Double bond somewhere. Does it matter which one? Not for this class. Okay? What else we got to do?
Down.
Put a bracket around it just to say this compound has a charge of -2. We good? Yeah? Do you want to try? Yeah. So you're not going to have to draw it. If it is on the exam, I will give you structures and say which one is correct. Right? Because it's multiple choice. That doesn't make it easy. You still have to know how to do it, right? So if I were you, I would draw it. Make sure you follow all the steps. Make sure you use all the valence electrons. Make sure they all have the octet. Say which one is the right one. Good? Yeah, Andrew.
So just to get clear on exactly what polyatomic ions are, I have it written that they're not ionic compounds.
They're charged covalent compounds. Now, having said that, if a polyatomic ion is in a neutral compound, what kind of compound do we have? Let me say that again. If a polyatomic ion is in a compound that is neutral, what type of compound is that? How do you know? Because it's neutral and it has an ion. It has a polyatomic ion in it, therefore it's made of ions. Every compound made of ions is ionic. But if we're just talking about a single polyatomic ion, well, that's a covalent compound. Therefore, if we have, let's say, H2CO3, carbonic acid, what type of bonds do we have in here? Ionic and covalent. You with me? Okay. Do we need to do another Lewis structure or are we okay? You tell me. Okay, I'm not hearing anybody saying let's do another one, but if you want to do another, let me know. Yeah.
So you said that one is ionic and covalent compound together?
Well, since it has a polyatomic ion in it, and it's neutral, that makes it an ionic compound. Now, this isn't both ionic and polyatomic ion or compounds. Sorry. This is not both covalent compound and an ionic compound, but it has both ionic bonds and covalent bonds. So if we have water, water has 2 covalent bonds. But for this one right here, we actually, you know how this is a, and you don't have to know this, guys, but you know how this is a -2 charge? This one's minus and this one's minus. And that's where the hydrogens are in this compound. Because the hydrogens are plus, so they're ionically attracted. So this right here is an ionic bond, and the rest of them are covalent bonds. So this one, and this one are all covalent bonds. Does that make sense? Don't it? That's right. Well, this is a nonmetal too. See, you got to kind of But since this is a polyatomic ion, this is also an ion. This is actually an acid. We haven't talked about acids. We'll get there today. Maybe. Okay?
There's a one question that is confuses me. Number 10. It's just sodium chloride you have to see, or there's some other things also?
No, so are you talking about number 10?
Yes.
Know which compounds dissociate in water?
We just use sodium chloride.
Sure, that's one compound. What compounds dissociate in water, guys?
Sugar.
All ionic compounds.
All ionic.
Does sugar dissociate in water?
Yes.
The answer is no.
Oh, right, that's not ionic.
Sugar is not an ionic compound. Does it dissolve?
Yes.
Yeah, we know it dissolves, and that's what. So just know dissociation and dissolving is not the same thing. What is dissociation? When they break apart. They break apart because they're ionically attracted. You throw them in water, and then they're surrounded by water molecules. We talked about this a little bit. Okay? That's what dissociate means.
But metallic also, like sodium chloride dissolves in water.
Yeah,
Yes.
because sodium chloride will dissociate
Sodium.
because it turns into sodium ion and chloride ion.
But the experiment we did, when you put in the water, it's
But if
It-
you add too
Metallic.
much, it doesn't get dissolved.
Yeah, it's only solubility to a certain amount per water, per liter of water, whatever. So what are you asking them on?
this one just says sodium chloride and all ionic compounds.
All ion. You wrote sodium chloride, right?
Yeah, I know.
Okay.
Sodium chloride.
All ionic compounds not. If a compound dissociates in water, it must be ionic. Write that.
But there's a metal is also ionic, but it's not some metal.
A metal is not ionic. But a metal with a nonmetal, together, it is ionic. Make sense? But if you just have copper, it's not an ionic compound, it's a metal. An ionic compound has a metal and a nonmetal, in general. What about this? Is that an ionic compound or covalent compound?
NaCl?
NH4OH. Is that ionic or covalent? Looks like covalent, but it's ionic. Who can tell me why?
Oh.
Because it's made of two polyatomic ions. Okay? An ionic compound is always composed of a cation and an anion. Always. Most ionic compounds are composed of a metal and a nonmetal, but not in this case. So, how do you know it's an ionic compound? If it's made of ions. If it has a polyatomic ion in it, or it has a metal in it. Can it have both? Sure. That's how you tell. We good? That's another reason you got to get your polyatomic ions down. At least have them up here. It's like, oh yeah, that looks like a polyatomic ion. I recognize it. That's a polyatomic ion. In fact, you need to know its name and charge too, right?
For example,
Yeah, go ahead.
talking about number 10,
Uh-huh.
then 24.
Okay, number 10 says, know which compounds associate in water. This is what we just talked about, right?
And then related with 24.
24. Know why and if compounds dissolve in each other or not. So, for example, let's do an example here. Let's say we have C8H18. This is gasoline, stuff we put in our cars. Well, some of us, right? And we have water. And if I take, okay, let's say I have sodium chloride. Sodium chloride is going to dissolve in which one of these compounds? H2O. Is it gonna dissolve in gas? It doesn't. Why doesn't it?
Not
Like dissolves like. Now, we don't call sodium chloride a polar compound, but remember this, gal? What's over here, guys? This is where sodium chloride is. So if we said this is polar and this is nonpolar, so salt is really polar. It really is, but we don't call it that. We just call it an ionic compound. But it is polar, and that's why it dissolves in water. Okay? Now, next, on Thursday, we'll talk about ionic compounds that don't dissolve in water. But right now, you don't need to worry about that. Okay? For exam 2, you don't need to worry about that.
You said like dissolves like?
Uh-huh. So polar dissolves in nonpolar substances. Nonpolar dissolves in nonpolar substance. What if we have oil? What do you think? Is it going to dissolve in water? No. Do you think it'll dissolve in gas? Yes, because gas is nonpolar. Can we see that it's nonpolar just by looking at it? We should, and let me tell you how. If we have a carbon-hydrogen compound and that's it, that means there's only two types of bonds. We have a carbon-carbon bond. Is that a polar bond?
no.
No, because the difference in electronegativity is 0. We don't have to look it up. We know it. They're the same element, right? So it's 0. That's a nonpolar bond. What about the carbon-hydrogen bond?
Yeah.
We can look it up on the electronegativity chart, right? This is 2.5 and this is 2.1. Difference is 0.4 and it's nonpolar. All carbon-hydrogen compounds, if that's all it is carbon and hydrogen, is nonpolar. Because who wants to draw the structure and the molecular geometry for that one? Not me. Right? It's really not that hard once you take organic chemistry, but we don't. Okay? Making sense? Or am I scaring you more? A little bit? Okay. So what, you guys gonna schedule to take the test this week or by Monday, right? Okay. Yeah. Sydney?
I know we just did Lewis structures, but can we do one for the acetate ion?
Yes.
Which one?
We had that for the lab.
It's,
Confusing me a
oh,
little.
did you?
Yeah.
Okay. To do this one, this one's not hard if you look. So there's two versions we can write acetate, right? We have C2H3O2 minus, and there's another one that's CH3COO minus. This is a
That's the one we had, the second one we had on the data sheet.
yes. This is the one we should be able to write the structure because it's written as the structure. We have a carbon with 3 hydrogens bonded to it. That's the CH3. And where's that C hooked to? A carbon has to have it doesn't have to have 4 bonds, but it has to have 4 electrons right here, right? 4 valence electrons. And then we have 2 more oxygens. One here and one here. If we draw the Lewis structure, in fact, let's just draw it out. Then we count the valence electrons. We have, for carbons, we have 8, another 3 for hydrogens, another 6 times 2, that's 12 for the oxygens. Are you following me? Plus another 1 for that charge. That's the valence electrons. Are you with me, or did I go too quickly? Too quickly? Okay. So that is how many?
24.
24 electrons. 2, 4, 6, 8, 10, 12. There's an oxygen here. Okay, so that means we have 12 more. Where do we put them? Around oxygen. 2, 4, 6, 8, 10, 12. Okay, we used all of them. Carbon doesn't have an octet. So we gotta have a double bond, don't we? Does it matter what oxygen you choose? No, it doesn't. We put it right there, and now it's perfect with a -1 charge. It would be a lot more difficult to do if they give you that one, right? I will never do that. Not in this class. Okay? So if I give you a multiple, so if I give you more than a binary covalent compound, I will give it to you in structure form. Kind of like I did with these ones right here. It's given to you in structure form. Do you want me to draw one? Or no? Yeah? Okay, so let's draw this one because that one looks icky, right? We have this carbon, has 3 hydrogens bonded to it. We have this carbon, 2 hydrogens bonded to it. We have this carbon, 2 hydrogens bonded to it. And then we have an oxygen with a hydrogen bonded to it. And if you count the valence electrons, there's going to be 4 extra electrons and they go there. You will not have to do that on the exam. Okay?
That's easy, so
Yeah, if I give it to you in structure form, it's not too bad.
you can do
Okay?
number 17 that I don't know.
Okay, did I answer everybody's questions up to this point? Okay, number 17 you said I'm on?
Some people also know.
And it's okay. No problem. Okay, number 17 says, know how to determine the electron geometry for a covalent compound. There's only 3 different electron geometries. What is if it's two regions? Linear. What is it if it's 3 regions? Trigonal, planar. What if it's 4 regions? Tetrahedral. That's it. Do you want me to draw them? What do you need?
An example.
Okay. So let's do SO2 is an example. If we draw this, oops, it's going to look like this. And we're going to have one lone pair around, one double bond. So how many regions do we have here? What? 3. Sorry. There's not 3 oxygens. It's going to be like that. Okay? How many regions do we have? 3. So the electron geometry is trigonal planar. It's going to look like this. What's the molecular geometry? Bent. Because molecular geometry, we're just looking at the bonded atoms. We good? Here's, finally brought some little models. And if you guys would like this, anybody have these? Would you like to use them on the exam? Okay. You're allowed to in this class, but I need to tell the testing center to let you use them. I didn't include that. Because every semester, then I brought some of these because we usually take the exams in class. And I have a table that says, you can come up here and look at these. And no one ever does. I don't know if you don't need to. I don't know. So there's tetrahedral. If you want to look at these later, you can. This is tetrahedral electron geometry, but what is it molecular geometry? Trigonal pyramid, right? There's the one we just did. It's a bent molecular geometry, but it's tetrahedral. Looking at this as the lone pair, right?
You mean trigonal plane?
Oh yeah. What did I say? Tetrahedral? Sorry, that's a trigonal planar. Sorry. Are we good? Yeah.
I know you just went over this, but I got tripped up on the lab questions because they asked for like molecular geometry instead of molecular shape or electron geometry.
The molecular shape is the same as molecular geometry.
Okay.
And sometimes it might be called, no, that's in a different class, never mind.
Easier way, is it just molecular is
The shape according to the bonded atoms. So like this one, there's only 2 bonded atoms, but there is a lone pair right here that's causing these to be bent down according to the Vesper theory, right? So we just call that the molecular geometry bent. Can you call it molecular shape? Yeah, sure. Geometry, shape, kind of the same thing, right? Did that help?
yeah, I just need to go over it 10 more times.
Okay. Yeah, make sure you get it down before you take this. If that's the part that's kicking your butt, get that little sheet that I gave you, zoom it down. I got that sheet on the internet, right? Well, you guys did I put that sheet on? I emailed it to you, did I? Maybe I didn't. Maybe I just gave you. But you look up Vesper theory chart. That's all I did in Google, and I found this one for you. You can take that, zoom it down, print it off, and stick it on your. Make sure you don't staple it so you can do both sides. No, but make sure it's glued on there so that you can't have access to the back side of it. Good? But again, you might want to get that down so that you're not, because later we're going to still need to know a lot of that. Go ahead, Mariana.
Yes, I have a question about covalent properties, the worksheet that we did.
Okay.
It's on section 3.
Okay,
Oh,
I should have brought that binder. I didn't bring the binder, so you're going to have to tell me what it says.
okay. The following molecules have been drawn to represent the actual geometric, so whether the following molecules are polar or non-polar.
Oh, okay.
So it's
Which one is it?
SO3.
SO3. And so it draws it for you, right?
Yeah.
Here we go.
I thought it was, so they're polar.
It's a polar bond.
They're bonds, but it's non-polar, correct?
That's right.
But why is it non-polar? Is it because they all?
Because, now, do you want the easy way or do you want the physics way? Do you want the real reason why, or do you want an easy way to figure this out?
Real.
The easy way
Okay.
to help in the test.
So we have to look at each bond. So we have 3 sulfur oxygen bonds, right? And so you look at the difference in electronegativity. What's the electronegativity value for oxygen? 3.5, right? What is it for sulfur? Is it 2.5? Look, 2.5. Okay. And so what's the difference? 1. Is that polar? Yeah. Okay, if it is polar, what do we got to do? We got to determine which side is partial positive and which side is partial negative. So which one is partial negative, the oxygen or the sulfur?
Silver.
Sulfur, because it has a higher electronegativity value. And makes this partial positive. This is partial negative. Same reason, right? Can we draw a straight line that separates the negatives from the positives? We cannot. Therefore, it's nonpolar. Good?
Which way will you draw a line anyway?
It doesn't matter. Let's draw a line. If we draw a line right there, we have negatives on both sides. That one didn't work. Well, let's draw right there. Oh, nope, there's negatives and negative. That didn't work. No matter where we draw this, we cannot separate the positives from the negatives. Can't do it. Therefore, it's nonpolar. Now that's if you that's just a quick and easy way to do this. Anybody want a deeper explanation? We kind of went over it, I think. Yeah. PBR3 looks like this. Right? Is that what it shows?
Yeah.
Okay. All right, so is the bromine phosphorus bond polar or nonpolar? Look at the difference in electronegativity. Nonpolar?
Isn't the 0.6 polar?
Okay, it's polar. But here's an easy way out of this one. Since it has a lone pair around the central atom, it will always be polar. Because there are some where you have a small difference in electronegativity, but the shape of it has precedent over the difference in electronegativity. But here we go. We can separate that. This is partial positive or negative? Which one's more electronegative? Phosphorus? Bromine? Okay, that's partial negative, partial negative, partial negative, partial positive. We can separate them. So right here, because of its geometry, all the negatives are down here and the positives up there. That makes it polar. Does that make sense to everybody?
Polar
Yeah.
because of
Yeah, so why is that different from the top example? If we were to do a three-dimensional...
This is three-dimensional. It looks like this. Trigonal planar is all on the same plane. So that is three-dimensional. You with me? But if we draw this one, right here, this one is the PBR3. Well, we can draw a line, because the line is infinitesimally small, right? We can draw a line between the negatives and the positives.
So only when we have 4 electron regions do we have to worry about the three-dimensional shape.
Uh-huh. It goes in 3D, yep. Did that answer your question? Any other questions? What? 15. Know how to determine number of lone pairs of electrons on the central atom of a covalent bond. So this is kind of in the process of drawing the geometry, right? So in this one right here, how many lone pairs are around the central atom? 0. A lone pair looks like this. And there's 0 lone pairs on the central atom. Yeah, there's lone pairs out here, but that's not the question. And when we determine the geometry, do we care about the lone pairs on the outside? No, just the central atom. Sure. How many lone pairs are around the central atom? Amon, how many lone pairs are around the central atom?
1.
1, right here. There's 2 electrons, but it's, let me say this. On the test, I believe it asks how many electrons, how many lone electrons are around the central atom. That's what it says on the test. What would your answer be? 2. Has 1 pair, but what does pair mean? 2 electrons. I don't like that question because we've been talking about lone pairs. So be careful, read careful. It says how many lone electrons.
The next class will be 3.
And how many bonded atoms around the central atom?
3.
There's 3 of them.
3 bonded and 1, 2 non.
3 bonded, 1 lone pair, or 2 lone electrons. Are we good with that? Anybody write that down? Because that is on the test.
That's why I asked.
It will ask, the way that it asks, a lot of people say that there's 1 because there is 1 lone pair. But it asks how many lone electrons. You with me?
Individual electrons or?
How many lone electrons? So if I says how many lone electrons are in this compound around the central atom, the answer is 2. There's 1 pair, but a pair is 2 electrons. I'm just telling you right now, that's what the question asks. So I just gave you one. Okay? But it's either that or just say, okay, I'm not going to count that one against you because it's worded goofy. Guys got it?
But this one we can say 2 lone pair of electrons.
1 lone pair of electrons.
1 lone pair of electrons, but the electron has 2.
See how there's 2 electrons in that 1 lone pair? Yeah. So read it carefully.
Yeah, that's.
And there's 3 bonded atoms. 1, 2, 3. Are we good?
3 bonded.
Anything else? Andrew? 22.
Through rank molecules can be used for most polar.
Okay, yeah. So if we have water, and we have CH2Cl2, and we have CH4, we want to rank these from least to most polar. And we kind of did that on that first question. Little bit different question, but kind of the same idea. So if we draw this, this is hydrogen bonding, right? This is dipole-dipole. And if you want me to, I will draw these. Just let me know. And this is London dispersion. So which one is the least polar? The one that's not polar, right? That's 0 polarity. And this is the highest. Because hydrogen bonding, why do we have a special dipole-dipole that's hydrogen bonding? Because it happens a lot in the human body, right? And why is it? What are the different atoms that could be bonded directly to oxygen? Or sorry, to hydrogen. Nitrogen, oxygen, and fluorine. These are the 3 that tells us it's a hydrogen bonding. Okay? Why these 3? Higher in electronegativity. If we have a bigger difference in electronegativity, that makes it what? More polar. You with me?
So in this one, which one is the most
Water.
water?
Why? Because it has a greater intermolecular force.
Like HB,
Hydrogen bonding.
So aren't those intermolecular forces and not bonds?
They're not bonds, but it doesn't ask. Now, We can do that one too. It says,
Oh, wait.
which one is the least to most polar
I guess I was
molecules?
also looking at 21.
But if it says bond,
is
if we have a carbon-hydrogen bond, we have a carbon-chlorine bond, and an oxygen-nitrogen bond, which one is more polar? So to do this, we have to determine difference in electronegativity, don't we? Carbon is 2.5, this is 2.1. Okay, that one's 0.4 difference. This one's 2.5, that one's 3. This is 0.5. This is 3.5, and this is 3. Oh, that's 0.5. That means these are the same, and that one's the weakest. Does that make sense? To have a greater difference in electronegativity, it's more polar. Talking about the bond itself. You can have polar bonds, but the molecule itself might be nonpolar, right? Because you can't separate the positives from the negatives like we showed before.
That's like question.
Do you have another
number
question,
10,
Andrew?
the same.
Kinda.
Yeah.
Just when it comes to making like the structures and stuff,
Uh-huh.
remind me, is it the most electronegative is usually the center?
Least electronegative. And it's usually the one that's by itself.
Yeah.
Okay? And the purpose of this course is to give you just kind of a basic knowledge of chemistry, but it goes deeper than 1010. So I don't think we make the questions really difficult. We make them quite simple, I think, as far as I remember. But yeah.
London dispersion.
Number 6?
26.
26. Know the different properties of ionic compounds, molecular compounds, metallic compounds, and covalent network. Okay, so this is what we talked about. Was this the last thing we talked about? Okay. So, ionic compounds. Do you know properties of ionic compounds? What about their melting points? High or low? High. Think about salt. Stuff we eat, right? You ever tried melting salt? Melting point is, you don't have to know this value, but it's 800 degrees Celsius. Very high. Then you get sugar, which is a covalent compound. It melts way lower. We can do that in our house, right? In our kitchen. Don't have to be very hot at all. So, ionic compounds have higher melting points. Covalent compounds, lower melting points. What about metallic bonds? Or metallic compounds? What about its melting point compared to the ionic or covalent? Higher. Takes a lot more energy to melt metal than it does to melt salt or a covalent compound. You with me? And then a covalent network, even higher, like diamonds. You're not going to melt your diamonds. Well, you could, but not a home for sure. Does that make sense? And there's other properties. Do you want more properties? Ionic compounds are malleable. Do you know what that means? You hit it with a hammer and it shapes, right? It just changes shape. It doesn't break. It's not brittle. But ionic compounds are brittle. You smack salt with, you have a big chunk of salt and you smack with a hammer, it's just going to shatter, right? Covalent compounds are, well, they could be brittle, like if it's sugar. It could be soft, like butter or wax. Those are amorphous solids, right? And then the hardness of diamonds, well, they're really hard. We use diamonds to cut metal, right? Anything else?
If you write this on exam, yes.
Yeah. Write all the words?
No, just an example, just change.
Okay, do you have a question, Rebecca?
Yeah, can we do number 6?
Number 6, yep. Know how to write the chemical formula and to name the ionic compound with a polyatomic ion. So, if we have CuNO3 2, for example, or if we have potassium. Okay. Oh. Let me do a different one. Okay, so here's 2 examples that you have to know. So we got to name this and write the chemical formula for this one.
Is it which question?
This one's number 6.
Number 6.
So to name this, what do we got to do? Figure out the charge of the transition metal. Because copper is a transition metal, so we got to figure its charge out, right? You guys, we did this a couple times already today. So this is 2 plus. So what's the name of this compound? Copper 2. Copper 2 what? Nitrate. This is nitrate. So you have to know the names of the polyatomic ions. This is carbonate. Is that a polyatomic ion? Yeah. So what's the chemical formula for this? What's the charge of potassium? And know that potassium's not P, right?
K.
Yeah. Look at the periodic table and look at the names. You have the periodic table, you use it. And it's in group 1, so it's K plus. What's the formula for nitrate or carbonate? CO3 2 minus. Now what do? Cross the charges and simplify. K2CO3. Do we need parentheses around CO3? No, because there's only one of them. Good? Ladies and gentlemen, next time we're going to be dealing with different reactions and predicting the products in the reaction. You have to be able to do this. So we need to know this for the rest of chemistry. Okay? Any other questions? You ready for a break and then what?
It's okay.
You sure?
Asking that.
Okay.
It's 13.
You want to do 13? Okay. 13 says, know how to name covalent compounds. What do we use? So covalent compounds are just like naming binary ionic compounds, ones with main group elements, right? We named the first one as the element name. The second one, change the ending to IDE. What else do we use for covalent that we do not use for ionic? Prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Got to know those. If you don't, you better write them on your little card. I told you to write a lot of things on your card. Mono means one. Di is 2. How are we feeling? Ready for a break? And then getting into exam 3 stuff after the break? Okay. Let's take a break. Do you have those prefixes?
Yeah.
Okay. Okay.
Thank you.
Did you have another question on?
I asked all question I asked.
Okay. Good.
I have a question.
Page with the electronic identity.
Let's see.
I don't know where's mine.
I don't think I have one here. But there is one on Canvas. If you wanted a paper copy, there is one on Canvas. Thank you. And again, you don't have to memorize that. I will give that to you for the exam.